So jet engines are awesome. And they're awesome in more ways than one. They're awesome in the normal sense of the word of just like, they're pretty neat, aren't they? And they're also awesome in the sense that they are awe-inspiring. They're loud. Powerful.
Which means Thanksgiving's right around the corner. You know what Hayden's favorite kind of turkey is? No, seared.
They make things go very fast. And they are technological marvels that make it so that we can go from pretty much any region on Earth to pretty much any region on Earth in less than a day's travel time, which is quite remarkable. Especially since that's just with the subsonic engines that we use on typical modern airliners. And given how ubiquitous and, well, just how cool jet engines are, there's no shortage of explanations of the basics of how they work. But along the way, there are some subtle misconceptions that tend to sort of creep their way in. And I want to go over the basics of how jet engines work today with a particular mind towards clearing up some of those misconceptions, but also towards just explaining the thermodynamics and fluid mechanics and the overall physics of how a jet engine works. And I'm mostly going to be focusing today on what's called a turbojet engine, because this little demonstration that I've built is actually technically a jet engine, but it is not a turbojet engine. And in fact, under the umbrella of things that we call jet engines is an extremely wide array of machines. There are, just to name off the categories, there's turbojets, turbofans, turboprops, ramjets, scramjets, and motorjets, which is technically what this little thing is. So what do we mean by all those things, right? Well, by jet engine, broadly speaking, we usually mean some type of an engine that creates a thrust, so a force used to propel a vehicle, by taking in some fluid, generally air, and expelling it out the back at a higher speed than it was brought in at. We could also more generally just say it's anything that uses fluid that is accelerated and sent out the back, which includes both rocket engines and jet engines under the sort of broader umbrella of a jet engine. Today, though, I'm going to focus, like I said, on turbojets, which, well, turbo means that something has a turbine, and a turbine is any machine that extracts rotational power, so, actual power on some sort of like drive shaft, like shaft horsepower or shaft kilowatts, from the motion of a fluid. And that's why wind turbines are turbines. They use the motion of the air to create power in the shaft that then drives the generator. So that's what makes something a turbojet or a turbine engine, is if it's an engine that utilizes a turbine. And a jet, we just said, is something that brings in air or another fluid and accelerates it out the back in order to create thrust. So a turbojet is an engine that does both of those things. So to start off, though, let's consider how thrust is actually created. And to do that, rather than show my sort of little demo engine blowing fire out the back again, which the fire out the back actually represents inefficiencies in the engine, I'm going to demonstrate the simplest form of jet/rocket propulsion, which is just inflating a balloon. Right? So when I inflate this balloon, the energy that we're storing in here doesn't come from the chemical energy the way it would with fuel, right? It's just energy that I'm storing in the balloon by doing mechanical work with my lungs and diaphragm to fill this balloon with air that's at a higher pressure than the outside atmosphere. And so as long as we keep the end closed like this, it's not going to have any thrust, because although the pressure is higher inside than outside, it's the same on every surface, and every surface is closed, right? Versus if I let go of the bottom of the balloon, it goes flying away. And that's, of course, because once the bottom is open, which here, I'll inflate this one too. Once the bottom is open, right, now we have this area on the bottom is no longer closed, but this area on the top is still is closed. And so the pressure is higher inside than outside, and as long as it's closed everywhere, all of the forces acting on the different surfaces cancel each other out. But as soon as there's this area on the bottom missing, now we have higher pressure behind the front of the balloon or the top of the balloon than we do outside the front or the top of the balloon. And once it's open, we no longer have anything at the bottom to balance that out, so we get thrust. So that's more akin to a rocket engine than a jet engine, where we have some volume that's open on one side, and we just take our fixed propellant, which in that case is just compressed air, and we expel it out the back at a high speed in order to have thrust. But mechanically speaking, the thrust is all coming from the top of the balloon here, where there's higher pressure behind the front of the balloon than there is ahead of the front of the balloon. And so if we have a higher pressure on one side of a solid object than the other side, then there will be a force on that solid object. Okay, that's fairly straightforward, but now I do want to bring up a couple more physics concepts that I'm going to use going forward, which are the connections between what I just mentioned about how we need higher pressure on one side of a surface than the other to get thrust, to the connection with Newton's second and third laws. And Newton's second law says that the acceleration of some object is equal to the force imparted on that object divided by the mass of that object, or conversely, the force is equal to the mass times the acceleration. And acceleration is the change in velocity in any given time, or delta v over delta t. Now, Newton's third law says that for every action, there's an equal and opposite reaction, right? So anytime thing A pushes on thing B pushes back with a force of the same magnitude, but in the opposite direction on thing A, right? So if our engine is, or for that matter, our balloon, is pushing on the air, then the air will push back on the engine. And so if we are changing the velocity of the air, we're accelerating it, and the air has some mass, then that means that we are needing to impart a force on the air to change its velocity, to accelerate it, and then by Newton's third law, that means we are going to get a force back on our engine. And so we are mathematically guaranteed by the combination of Newton's second and third laws that if we accelerate some mass of air, we will get thrust. And when we do that for a continuous flow of air mass instead of individual masses of air, we get that the force or the thrust is equal to the mass flow rate, the amount of mass of air being pulled through the engine in a given amount of time, times the change in the air's velocity between when it's entering the engine and when it's exiting the engine. So mathematically, Newton's second and third laws combined ensure that we get thrust as long as we're doing that. But remember, to actually get that thrust as something we can use in our engine and our vehicle, we need some solid surface where that's actually happening. And, because Newton's second and third laws are going to apply, we can be assured that is happening somewhere, but I think it's useful to sort of track down where exactly it's happening. Now, like I said before, I'm going to be talking about turbojets today. So in the case of a turbojet, we have 4 steps. We're going to have compression in the uncreatively named compressor at the front of the engine, which is going to be what we call adiabatic compression, right? So I'll be showing an animation for what's called an axial flow engine, but there's also what's called a centripetal flow engine, which is just where the air is flung to the sides and then hits the walls of the engine instead of being sent through alternating stages of compressors and compressor blades and compressor stator vanes. And axial flow engines tend to be more powerful and more efficient, but centripetal flow engines are simpler and can be made much smaller. So we first compress the air in the compressor, and when I say adiabatically, what I mean is we're not letting any heat in or out when we do that. And a result is because we are doing mechanical work on the gas as we compress it, it's going to heat up. So we're going to increase the pressure, increase the temperature, and increase the density of the air all at once without adding or removing any heat. And then the next thing that's going to happen after that is the air is going to pass from the compressor into the combustor. And in the combustor, we're going to add fuel and we're going to combust it, burn it, in order to heat up the air. But that is actually what we call isobaric heating, which is to say that the temperature of the air inside the combustor is going up, but the pressure is actually a constant. And it makes sense if you sort of look at it. The combustor is open at both ends. Right? The compressor isn't really sealed either, but the compressor is able to use some fluid mechanics effects to have a sufficiently big change in velocity in small spaces that the air is going to get compressed and it can sustain a pressure difference. But the combustor has pretty much the same width throughout, and it's open at both ends, so we're not able to have a pressure difference between one side of the combustor and the other. What we will have is a tremendous increase in the air's velocity, because when we burn the fuel in the air, we are going to raise the temperature, and if the pressure is constant, but the temperature goes up, the density actually has to go down. And if the density goes down, but the area of the tube it's going through is constant, then that means it has to speed up. So we've now done adiabatic compression, and we've done isobaric heating. And so then the next thing is going to be the turbine, which is what makes it a turbojet. And in the turbine, we kind of do the converse of the compressor, where now, instead of doing mechanical work on the air to compress it, now we're going to extract some mechanical work from the air as we let it expand. And we let it expand through a few stages of turbine, which how many stages there are depends on the design of the engine. And it's going to slow down, it's going to cool down, and it is going to drop in pressure. Now, after we've done all of that, we are finally going to exhaust the gas out the nozzle, and thermodynamically, the nozzle doesn't really do anything, but fluid mechanically, it is going to speed the air back up a little bit. And finally, after it leaves the nozzle, well, what actually happens, and fluid mechanically this is important, is that it just exhausts out the back at high speed. Because remember, if we change the speed, the velocity of the air between when it comes in and when it goes out, we are guaranteed to get thrust by Newton's second and third laws. And thermodynamically, we then bring in fresh air, which is thermodynamically equivalent to taking that air we exhausted and cooling it back down to atmospheric temperature. Now, in reality, of course, the exhaust is just going to flow out into the atmosphere because the Earth is just one giant heat sink, or the Earth's atmosphere is in this case. And it will mix with the ambient air and we'll just ingest fresh air, but thermodynamically that's equivalent to isobaric cooling, because one of the things we want to do in the nozzle is to bring the air back to 1 atmosphere of pressure, which thermodynamically we model that as expanding it in the turbine until we've adiabatically expanded it back to 1 atmosphere of pressure. It will be warmer than the outside air temperature, and so that's thermodynamically equivalent to isobaric cooling. So, having said all that, here's a question. Which of those 4 stages, the compressor, the combustor, the turbine, and the exhaust nozzle, where is the thrust coming from? So, you could make an argument for the combustor, but you could also make an argument for the turbine and for the nozzle. But mechanically speaking, the thrust is actually coming from the compressor, right? Because remember, if we want thrust, we need a forward-facing surface with higher pressure behind it than in front of it. And the combustor is where we're adding the energy to get our thrust by adding the fuel and burning it. And the turbine is where we're extracting the power that we need to run the compressor. But the only place where we have a difference in pressure and where that pressure difference is actually going the right direction is in the compressor. And for an axial flow compressor, you can actually kind of see it because the compressor blades look very similar to the blades of just an ordinary propeller, right? And they are similar, except, of course, they're not being used to accelerate the air. They're, in fact, the reason that the stator vanes are there is so that we can repeatedly stagnate the air and increase its temperature, pressure, and density while not accelerating it too much. So we then are left with the force coming from the compressor. So that's where the thrust, strictly speaking, is actually coming from. And everything is satisfied because this is where I have to mention that this is all for subsonic airflow. The pressure in the combustor is able to travel upstream to the compressor, right? There's no difference in pressure between the entrance of the combustor and the exit of the combustor, but the pressure at the entrance to the combustor is the same as the pressure at the exit to the compressor, and the compressor does have a pressure difference across it, and if we raise the overall pressure in the combustor, then that will result in a higher pressure difference across the compressor blades and the stator vanes, which will give us more thrust. And of course, we can't get energy from nowhere. Thermodynamically, we need to run the Brayton cycle to completion, and we need to get the power to actually run the compressor, which we are going to extract at the turbine. And so in a turbojet, we are using our thermodynamic exhaust, right? The fluid that we actually compressed and then heated up and then expanded in order to run our engine cycle is also providing our thrust, but the place that's happening is actually the compressor. And in that sense, there's two other kinds of engine that are more similar to a turbojet than you might think, which are turboprops and turbofans, right? And so turbofans have this is just a little 3D printed model of a fan, right? These look just like propeller blades because that's basically what they are. And in a turbofan, we have some additional stages in the turbine that extract more energy from the exhaust and use that to run the bypass fan. And so we're still getting some thrust from our exhaust gas, but because we're slowing it down, and mechanically that's taking the form of the turbine adding extra drag in the exhaust stream, but we're then using the shaft power, or shaft horsepower / shaft kilowatts, to drive this big diameter fan, which is going to accelerate a much larger quantity of air, right? The thrust is equal to the mass flow rate times the change in velocity, and the change of velocity we get from this fan spinning is lower, but the mass of air it can move is so much larger that it turns out that for subsonic speeds, this is a much more efficient way to get thrust. And a turboprop is basically the exact same thing, it's just that it's using a propeller with long propeller blades, and typically, 2, 3, 4, maybe 6 of them, as opposed to, the many blades on a ducted fan, and there's no duct on the outside, right? There's no engine cowling around the edge of the propeller, but other than that, a turboprop and a turbofan are essentially the same, and turboprops and turbofans both get some thrust from the actual exhaust of the turbine engine that's in the center developing the power to spin the fan or the propeller. Just nowhere near as much as a turbojet, but in some sense turbojets aren't that different because they're also getting their actual mechanical thrust from the compressor. It's just that in a turbojet, the entire volume of fluid is pulling double duty as being both the fluid we use for our engine cycle and the fluid that we are exhausting out the back to get our thrust. And it's worth noting that we have two processes to keep track of the efficiency for. We have the actual thermodynamic efficiency of the Brayton cycle, which is related to the pressure ratio across the compressor, and we have the efficiency of then taking the usable work that we can get from the Brayton cycle, which is limited by the laws of thermodynamics and it cannot exceed the Carnot efficiency. But we also have to consider how much of that usable work is used to create thrust. And it is true that the faster you go, the less thrust you will get for the same amount of useful engine power. But even within that, we have inefficiencies due to the way in which we accelerate air to create thrust. So, high bypass turbofans are better on both accounts because they improve the pressure ratio of the engine core by providing additional cooling, and they also improve the efficiency to a much greater degree in that second step, where we're actually taking our usable work and using as much of it as we can to actually create thrust. So that brings me back to this little demonstration engine here, which it's a bit of a stretch to call this thing an engine, but it by definition is, right? Because it has a fan up front here, but this fan is just driven by an electric motor, and when the electric motor spins, it pushes air back through this, and this is not intended as a nozzle, it's just because this was the sizes of motor and tube that I could get. And so this little electric speed controller pulls energy from a battery to spin the fan, and then it reaches this tube back here where fuel is added via this tube here, and then I introduced spark with a little igniter here. And then it burns inside this combustor tube, and when it does, the pressure does increase, but it doesn't change between here and here. It increases the pressure everywhere inside the engine, which causes there to be a higher pressure right behind these fan blades than there would ordinarily be. Because normally the reason there's higher pressure on the fan blades is just that they're spinning through the air, and as a propeller spins through the air, right, it's moving, and as it does, the air hits one side and it gets deflected downwards, and I could have a whole other discussion, and probably will sometime, about how wings and propellers work, and it's relatively straightforward, though, why a surface at an angle relative to the air is going to push air downwards like that. And so, again, by Newton's second and third laws combined, we're going to get a thrust. What's not so obvious is why this particular shape that propellers have is so efficient. And so we're getting additional thrust, though, on our fan/propeller by merit of the fuel increasing the overall pressure and temperature, even though it exhausts at 1 atmosphere. And the pressure right behind, well, ideally it should exhaust at 1 atmosphere, because ideally I would put a nozzle here, but this thing is already... I don't like to do things that are too sketchy, because I hate being, the person that's like, don't try this at home, but seriously, don't try this at home. I've done as much as I can to make this within a reasonable degree of risk, and this thing is not super hazardous. It would be more efficient with a nozzle back here, but I don't want to do that because the thing that keeps this some semblance of safe is that everything is nice and open. So if there's a buildup of fuel that suddenly ignites, it won't cause a pressure buildup. It'll just all shoot out the back, which not fantastic, but will not cause a disaster. So the pressure inside as a result of the fuel burning is going to cause there to be a larger pressure behind these fan blades, which will increase the thrust. And of course, it doesn't increase it by that much, at least not relative to the amount of fuel that it consumes every minute, but it's just sort of a glorified blowtorch that nonetheless does technically qualify as a jet engine. So that's how that little pressure jet or motor jet works, and there were some early jet aircraft that did use motor jets where the compressor was driven by a piston engine and then they used a separate combustor and no turbine. There weren't very many of those because they are horrendously inefficient and not really worth the weight and complexity relative to just using a piston-driven propeller. You might as well either do that or go for a real jet engine, but for a little demonstration purpose, this works perfectly well. So that's how everything works for subsonic airflow. I will cover supersonic airflow in the future because I want to keep these to a more reasonable length. And when you have supersonic airflow, now pressure can no longer travel upstream, right? So if the airflow here were supersonic, it would be unable to add any pressure up here. But once the airflow is supersonic, then there's some other clever things you can do to develop additional thrust. And so next time, I'll be going over how the engines on something like an SR-71 work and how they're able to use shock waves to improve their efficiency, and also how you can have something like this, which is a 3D printed model of a solid-fueled ramjet, which is the Meteor missile. And it's going to be the same thing, which is where if we compress the air and then add energy to it by burning some fuel and heating it, and then expand it, we are able to run an engine cycle. And when we're doing that with supersonic airflow, there are some clever tricks that let us still get quite a lot of thrust. But that's its own sort of can of worms that we will open at a later date. So hopefully you found that informative. Please do let me know if you have any questions. I do always appreciate the other sort of things, like, well, if you want to subscribe and see part 2, go ahead and do that. But that's, if you would like to see more of my videos, go ahead and subscribe. Obviously, liking does just sort of help me out. That's the only thing that's purely just if you want to give this a boost, then you can click that little button. Subscribing is if you actually want to see more of my videos in the future. But one thing is, if you have any questions whatsoever, please do ask, because I do this for many reasons, but the biggest reason by far is that I love science and engineering, and I love to explain things, and I love to answer questions about science and engineering. So I guess, feel free to comment anything you'd like, but I especially love answering questions. So if you have any, please do ask, or if you think I made any mistakes, please do let me know, and I will endeavor to correct them. So yeah. Thanks for watching. Bye.